and welcome back. So 1 down, 3 to go. Let's take a look at what the assembler does. So again, here we are in the big picture. The assembler's job is to take in the .s file. That's that assembly language program, the RISC-V that you've written, that you're learning to write from the last couple of weeks. And the goal is to produce object code, .o. And you're going to ask yourself, and hopefully you'll see from this, why do we do this? Why don't we just go straight from the assembler to produce the actual executable? You're going to see what there's a two-step process, and it does help to have a layer of linking in there. We'll explain that a little later. So again, the input to the system of the assembler is .s file. That's RISC-V if you're in that ISA. The output is object code, and this is going to contain tables. And really that's the reason. The reason we don't just go straight there, because we want these information tables. To be able, and part of this is to be able to have lots of different, a big program broken into lots of .c files. Each of the .c's compiles down to .o's, and then those .o's at the last stage are linked together to make one executable. And that is really the benefit of having these 3 layers. We'll talk about that when we see that picture. So the assembler also is going to read and use directives. We'll talk about that in a slide or two. Replace the pseudo instructions. You learned about that last lecture. The pseudo instructions like move, T1, T2 gets replaced by the add I instruction. Our goal is to produce the machine language, .o files, and create the object file. So what are some directives that we have? So some of the directives we have are here, listed here. These 5 directives tell the system, it's not a line, it's like a directive. It's not a line, I mean, it is a line, it takes up a line in the code, but it says what to do at each of these stages. So .text says the following, from here till the next time you see a directive, this is going to go in the text segment. That's the machine code. That's the actual code that you ran. You ran this down in the actual hello world, add 1 to 2, subtract, load word. That is down in the .text segment. The .data says to it, from the following is going to be data I'm going to use. If you have a big array, that'll live in the .data section. .global with the symbol says this is the space in the static area where the following symbol is going to live. .string says the following is just text string. Take it literally as that. You'll see that at the end of the lecture of that. And .word, if I want to store some values there, some raw memory words, I'm going to store those in the .word area and label it as such. So we saw the first one. We saw the first example of a move, which gets translated to an add I. That's not magical, and you saw that before. How about negate? I take T1 and negate it. It was a +5, I want to make it -5. Kind of nice. I don't have to worry about how to do that. Here's how you do that. You take 0, you subtract T1 from it, and now that's 0 minus T1 is -T1. Store that in T0. Same idea as negate, but a little easier to write negate than it is to write the sub thing and maybe get the order wrong. No, just call it negate. Negate T1, put it in T0. Next, load immediate, LI. That says load this immediate and directly put it into T0. Now you can realize that that's the same as saying add I immediate to 0 and then put in T0, but it's kind of nice to have just load immediate directly. How about not? This is the bitwise not. This isn't not a single bit. This is 32 bits of not. Okay, so how do you do that? Well, you XOR with -1. What does -1 look like? You may know what -1 looks like in 2's complement? Yeah, all ones, all ones, all ones. So you take all ones, and if you XOR with that immediate, XOR says, if it's a 0, keep it. XOR says, if it's a 1, flip the bit. So this flips the bits of all of T1, and all of T1 bits get flipped and get stored into T0. Pretty cool. So now you get to say not, and that's a 32-bit wise not. Love it. Branch if equal to Z, 0. If T0 is 0, then you branch if that's equal to that. So you branch if T0 is equal to 0, meaning I branch to the loop. So here's another way of saying it. Branch if equal T0 to 0. Does T0 equal 0? If so, branch to the loop. Same idea as saying branch if equal to 0, T0. Just again, a shortcut way of doing that. I'd much rather write the code on the left than the code on the right, and that's what's nice about having these pseudo instructions. Load address. So I've got an address here, and I want to store that in T0. Where does this live? Where does that label live? Load that address into T0. Sounds great. Well, there's 2 ways of doing it. You can load upper immediate, which loads 20 bits into T0. Okay, so I'm going to take the 20 bits, the upper 20 bits of that label, and put it into T0. And I say, you know what? Now I also need to stuff the lower 12 bits. How do I, so now I've kind of slammed in 20 bits on the high side. How do I store the lower 12 bits? Well, add I. You know, it kind of makes sense, right? You know that there's no way for me to, in one instruction, take 32-bit, not only have the instruction, have the register label, and have the string itself. I mean, have the label itself. That doesn't make any sense. So I say, I'm going to take the top 20 bits, do it in one stage, and then add I, the lower 12 bits, by saying add I that to T0 and put it there. So that's it. Or I could do another thing. Both of these are similar, but they're different in a subtle way. Add upper immediate to the PC. This is a PC relative operation. Same idea. So the bottom is the same, this is the same, but add upper immediate is a PC relative operation. Again, two ways to say load address. One is more static addressing and one is PC relative addressing. So don't forget the following. We've got to sign extend our immediates. So this is an immediate, this is an immediate, this is an immediate here. This is an immediate, okay? Those have to be sign extended because add I in the actual data path, and when we build the machine, we're gonna see this in the next lectures, when we build the machine out of this, I can't just add 12 bits. I've got to add 32 bits to 32 bits to get 32 bits. So how do I take a 12-bit value and make it 32? I've got to sign extend those guys. Don't forget also, this is another important part, that when I'm branching, I'm counting by the half words. That's one of the RISC-V features. Some might say misfeatures, where you're counting by the half words, not the words. So, all right. So now you've seen we've done the first stage, which is replace our pseudo instructions. The next step is we've got to produce some machine code. Okay. So the object file. So what do we do from my object code? Well, if I've got some simple cases, the simple cases is always the adds. The add, subtracts, logical shifts. They're just numbers. We could play with that. And all the information I need is in the instruction. 32 bits tells me everything I need to know. Don't need to do much about those. What happens when I get to branches and jumps? Well, those are PC relative. Okay, whenever you have PC relative, you got to query what the PC is and then use that somewhere in that process. So here's the nice thing about that. Once my pseudo instructions have been replaced by real ones, sometimes one becomes two instructions. You saw that before. But once that's been done, I know the relative distance between where I am and where I want to go. So if I have a branch of equal and I need to be counting by those half words, I can now, I know exactly how far away to be able to then count by half words, how many half words to jump there, to branch there, and then replace that number. So I actually can replace that number. I'm pretty happy with that. So those are handleable, meaning at the when I'm done with the .o file, those final values are there. I don't need to wait for some later stage. So I can just count those numbers, put those numbers in that field, and I'm done. How many half words do I need to branch? I'm done. So that's actually easy. So far, this is the easy case. This is one of the challenges we have. What if I'm branching forward? Well, that's nice. You should be able to branch anywhere, right? I should be able to go here and branch there and branch there. You know, if I had a go to, that's a different thing. But the point is, I want to branch. I want to do a branch here, and I have a label, and I want to branch. But what if? And here's this piece of code that says, you know, set T2 is 9. If T2 is greater than 0, it's set less than. And if T2 is less than or equal to 0, go to L2. Otherwise, I subtract 1 from T2 and then jump back to L1. So this is a little loop that does something. Well, by the time I get to here, I'm going to L2. If I'm walking down, okay, a single pass, I'm walking down, I got here, okay, L2. Problem is, I haven't seen L2 yet. I'm walking down, line 1, line 2, line 3, I don't even know where L2 is. It might be an error. L2 maybe it was hand-coded by a student and it says an error, and L2 is a label that mistyped it. It's not there at all. Well, that's going to be a challenge. What happens when L2 is below? What happens if it does exist, but it's below? Well, here's how we have to do. We have to make 2 passes. So we can't just count one by one, a one-pass system, one by one. I get to a label. If I haven't seen it yet, if it's a label I've seen before, I get it because I've already replaced the 2 instructions. I'm walking my way down. I've seen it before. Okay, that's the line. I can count back, and I got that. No problem. I make a note of where it was. I can go back. But if I haven't seen the label before, that's going to be a challenge. So one pass is, so what we do is 2 passes. The first pass, well, 3 passes. The first pass is replace the pseudo instructions. The second pass is make a note of where all the labels are. The third pass is when I see the label in the branch, now I know where all the labels are. That was the second pass. Well, I said the third. There's 2 passes to do this. And the first is you can replace and remember where the labels are. But the idea of all this is the second, what we call it 2 passes. We don't really count the replace the pseudo-instructions as a pass. We do that. And now I have 2 full passes. Once that's done, go 1, remember the labels, go 2, and now if I see a label, I know how far in half words to go forward for my branches, okay? So I've got that covered. Second pass is notes where the labels are and then puts the number in. Now I can hard code what that branch value is, and I'm done. So that's pretty cool. We cover that case now. Here's an example here. Jump to L1, jumps back 3 words. So that's 6 half. I'd store 6 there. I'd store actually -6 there. And this says 3 words forward or 6 half words. I'd store +6 in that branch value there. Okay? How about this one? What about PC relative jumps and branches? So here's jump offset. If I say jump to this offset, it's a pseudo instruction. It actually expands to jump and link 0, write something to 0, it doesn't change it at all, and to that offset, okay? So again, this is great. This is also position independent code, PIC. I just count the number of half words between the target and the jump, and I'm ready to go. So this is a PC relative jump. Anything that's PC relative, when you hear the word PC relative, that means position independent code. Because my PC is something that works with me. I'm here, I'm here, I'm here. Program counter tells me where I am. PC relative says relative to where I am. It's not absolute, it's relative. And so those relative things are great. That produces position independent code. We love position independent code because I don't have to move it later. I can now, if it happens to get relocated someplace different, it's still relative to where it is, and it's -3. And -3 is going to be wherever. If I end up moving this piece of code up and down in the final location, it doesn't matter. -3 is still -3. From this finger to this finger, still is those -3 as I move it in a global position in the final A dot out. So that's great. How about a reference to static data? So load address becomes a Louis add-I. If I want position independent code, I talked about that before. I want to use the add up or immediate. But if I use a Louis add-I, these require the full 32-bit address, the final resting place, not relative to where it is in my .o file, but the final resting place in A.out, and that's going to be trouble. So that isn't position independent code at all. So those we can't determine yet. A Louis add-I we cannot determine yet. We can add upper immediate PC, but we can't for a Louis. Okay. So here's the idea. We also need to build some tables. Sometimes .c becomes .s, and then there are some symbols that can be used, like an extern, by another C file. So I need to be able to know which symbols are available to me. So these are any labels. If I have a function here, and I want to be able to jump to this function call. I want to, call that function. And another guy, I need to know that label in this function, in this program, can be called by this .c program. Okay? If you load math.h and you want to call sign, you didn't write sign. Sign lives over there in math.lib, math.a. So you need to be able to get a label of does sign exist there as a symbol I can use. So every time you produce this object code, you have to declare what are the symbols that people could use, could jump to, could call to. Also, there's some data that I have that people are using. Let's say I have a global array that's going to be used by this .c file. You shouldn't have to copy that global array here. You should be able to reference it. So how do you reference that external guy? So you want to be able to reference the labels and some data from external files. That's the idea. So labels and data are two things that you have in your symbol table. The relocation table is the table of things that are to do. Remember, if you can directly write the 32 bits, write them out. Add, just write it out. I have all the things I need, go. PC relative, I've got all I need, go. After you've done that, the 2 passes we talked about before. But there are some things I need to know the actual absolute address of where things are. And I can't know that until I finally have what we call the final resting place in the A.out, in the final executable. So the relocation table says this is where it's almost like you put in a star saying to fill in later. The relocation table is the list of things you need to fill in later when you finally link them together. In fact, that's what linking means. Link means fix those link addresses. Fix those things like where I say to do work later. Star, do work later here. That's actually what the linker is going to do, is fix those links. So anytime I have an absolute label by a JAL or JAL-R, those things, or an LA, I need to be able to know what the final location is to be able to load that address into it. And it's not about relative, it's the actual address in the final resting place. Also, any data in the static section. If I have data in the static section, I don't even know where the static section is at this point, at the level of the assembler. I don't even know where that static section is. That's the job of the linker to kind of create that. So all of that's going to be done and labeled and going to be put on the list of to-dos in my relocation table. Okay? Symbol table is the things that could be called in my program, things that could be called, or my data that's going to be exportable, or my labels that could be called into. That's my symbol table. My relocation table are all the ones that I didn't really have the final values there. So make a star and add them to the relocation table so that somebody later, the linker, will replace those and fix those later. Pretty cool. So last slide. That was a big piece. This is a long, I'm like 15 minutes into this lecture now. The object file format contains, almost by the way, all file formats you've seen have a header. You saw PPM in your project that had a header. So the header it tells you kind of what's the size of things, like the following file contains, the following movie contains, blah, blah, blah. The following file contains the following pieces, and they live here, 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 and here, so you can just jump into those guys. What's the text segment? What's the machine code? What's the data I'm using? What's all the raw data I'm going to be storing? All those strings, all the hard-coded Fibonacci series, the first 1,000 Fibonacci's, that's in the .data area. That's stuff that's going to be there, be usable, it's hard-coded data, put it right there. I have my relocation table. Again, relocation is the stuff to fix. The things I didn't have those absolute addresses, I need to be able to fix those. That's like the work to do. Symbol table, what are all the symbols that other people can call into me to get access to my functions or my data? Any debugging information. Remember we talked about the translator says, hey, let's do some work and add more debugging information. That can be a ton of stuff. So all the debugging information is also in the object file format. That's all .o. And for example, a standard file format is ELF, and here's a link to that, okay? Next up, the linker. We'll see you there.